Okay, welcome back to part 2 of the lesson. I'm going to note that this form is also equivalent to what you'll see on the next page, which is minimize B vector transpose Y subject to A transpose Y vector. I like to keep my Y's consistently written. Which is greater or equal to the C vector, and then Y vector is greater or equal to 0. Remember, this is a vector equation. This is M inequalities, as is this. Oh, this is M, sorry. This is N inequalities. Okay. Anyway, and you can see that that's what's written here. I derived the dual out from this primal and got out this dual here. And I'm just going to note that this is the same as writing Y transpose A is greater or equal to C transpose. If you remember your transpose laws, this is following from the fact that if you take AB transpose, it's equal to B transpose A transpose. Okay. Anyway, so the first theorem we're going to start with is weak duality. And what it says is if X star is a feasible solution to the primal and Y star is a feasible solution to the dual, then you have that the objectives are bound. And of course, this follows just from the Lagrangian inequality, which we can now write out. It's C transpose X star, right? Well, what's true? What's true here is that in the dual, I can use the dual expression and I can replace it seeing this equivalency. So now you start to see why I wrote out the C transpose. I can say this is less than or equal to, well, C transpose is less than or equal to Y transpose A, right? That's just from the fact that Y star is feasible. So Y star transpose A times X star. Okay. Let me just write this a little neater here. Okay, well now I can use associativity. This is equal to Y star transpose times A X star. And now I can use primal feasibility, right? And substitute in B. And I get that this is less than or equal to Y star transpose B. Right, so this one used the fact that C transpose is less than or equal to Y star transpose A. That's dual feasibility. And this used the fact that AX star is less than or equal to B, which is primal feasibility. Okay, and of course that's exactly what we want because this is equal to B transpose Y star, which is the statement of the theorem. Okay, this should not be surprising. This is the basis for taking duals, guarantees this theorem, right? right? The whole point was we were deriving bounds. So this is just formalizing the bounds that we got. The consequences of weak duality are immediate, though. If, for example, you have a feasible solution to P, X star, and a feasible solution Y star to D, and you have this, so not just that they're less than or equal to, but that they're equal, then you have optimal solutions. And, well, why is that? By weak duality, any solution X to P that is feasible has C transpose X less than or equal to B transpose Y star, right? Because Y is dual feasible. But this is equal to C transpose X star by the assumptions of the theorem. Thus, X star is an optimal solution. And of course, the same holds true for Y star. Similarly, for any dual feasible Y, in other words, to D, that is, B transpose Y is greater or equal to C transpose X star, because Y is X star is primal feasible, which is equal to B transpose Y star by the assumption of the theorem here. Okay, so Y star is an optimal solution. Remember, X star is to P, and Y star is optimal